Hi all, thank you for coming today. Let me welcome you to the first speaker, Nguyen. So she's going to talk about scale smarter, not harder with cuPyNumeric. Welcome, Nguyen.
Hi, thanks Sean for the introduction and everyone for being here today. So Irina is an engineer at NVIDIA and I am Quynh. I am a staff scientist at SLAC National Accelerator Laboratory in Stanford University. So today I'll be talking about a collaborative work that we've been working on together with a bigger team on how to use cuPyNumeric to accelerate data computation for science. So let me first start off by saying the whole talk that I'll be giving today, it's applicable to a much wider field of science, ranging from planetary all the way to chemistry. And of course, there's biology in the middle, so we're going by scale here from really big to really small. And my expertise is focusing on material science. So I will talk to you primarily about material science. How do we use X-ray free electron lasers to study these items, and how do we use GPU computing platform to make them go very, very fast and enable us to see even more things that we haven't been able to see before. So I'm sure a lot of you are familiar with this picture here, which is a silicon wafer. And on this silicon wafer, you can find billions of transistors. So imagine, or for example, in a CPU, you can find several billions of transistors. So now what we want to do is we want to scale up electronics to even higher. How do we make even better electronics, even higher performing? One way to do it is to break down these 3D materials into different sections. So if you treat it like a big Lego piece, what we can do is to peel layer by layer and put them together the way we want to modify the electronic properties. So I'm sure you have played with Legos at some point in your life. And you put the pieces together the way you want. So we apply the same idea to materials. Imagine if you go to a restaurant and you see a menu. There are different items on the menu, and you can pick several of them and put them together. So in this case, what we can do is stack different materials in different configurations, and this way you can choose the exact properties that you want to have and design the electronics that you want to have. This is a capability that allows a lot of flexibility and enable us to do things that we haven't been able to do before. So for example, you can tune the way electrons move or current is generated by tuning the shape of the material or structure the material differently. So, but there are challenges that come with this ambition. One is, okay, we can put these electronics together or these materials together, but how do we know what properties they have? And how do we change their properties when we put them next to each other, which is likely will happen. The next step is, after predicting these properties, how do we make them? It's a very complicated and lengthy process to actually make high-quality materials for devices. And then the big bottleneck at the end is, okay, now I make these devices, do they actually function? Or would they just collapse within a few minutes or a few hours? So I go to a lot of facilities in Europe, from DAISY to Switzerland to DAISY's in Germany, or all the way to Japan, and every time we have to ship devices or materials across overseas. So this is something that we think about a lot. Would it survive on the plane? But luckily, there are multiple efforts that are ongoing that help addressing these issues and advance the field of electronics. So one of them, notably, is the AI-driven material prediction, driven by a public-private partnership between Pacific Northwest, Microsoft, and Micron. where they use AI generated to predict these properties and what happens to the whole stack of materials when you put them together. And this allows you to see your imagination being calculated and how does it change. The next step is the collaboration between Google DeepMind and Lawrence Berkeley National Lab, where they have a robotic-driven AI that makes hundreds of thousands of these materials every day. Given that the Microsoft and Pacific Northwest and Micron can predict millions of materials every day. The big question remains, how do we know that these can survive and these are real? Because a lot of them, they don't actually exist or cannot exist. Where do we come in? So SLAC has a unique tool where there's an X-ray, and we can use it to look at different materials. And in this case, but for an experiment like this is complicated, and what we would need is accelerated computation to help us run faster and look at more detailed data that we haven't been able to do. So let me first walk you through what each of these, how do we do each of these experiments? And then I will tell you how we apply the computational tool to improve it. So each of these involves many different components. They're complicated, generate massive data, and of course, require very demanding data analysis process. And up until this point, we typically use Python and Python libraries to process all of these data on hundreds of terabytes data scale and compress them down to hundreds of gigabytes or even smaller, and then perform the analysis on these. And we selectively do the analysis because we're just limited by bandwidth and computational time, and some of these computations are just completely not doable or not realistic. So we work with our NVIDIA collaborators, specifically the cuPyNumeric team, to implement Python or NumPy libraries onto which allows us to do implicit parallelism and enable a lot of these calculations to run on a much faster timescale. So I'll go into a little bit more detail on this, and if you attended Jeremy Tanner and Andy Terrell's talk on Thursday, Andy also talked a little bit about this. So what is a free electron laser? So the first one for hard X-ray was built at SLAC National Accelerator Laboratory, which is a part of Stanford University and the Department of Energy. It's a very lengthy thing that's about 3 kilometers long. And you can find it under 280, so if you fly into SFO, about within 30 minutes within landing, if you look down, you can see this really long and straight thing. That is the linear accelerator. And every year we have an annual 5K, so we basically run up and down along the accelerator. And this accelerator applies to many different things, many different objects that allows us to do discovery science that cannot do anywhere else. So let me tell you why that is. So I think about it as a very fancy camera. So a lot of you have seen this in your introductory physics class from a while ago. It's basically going from very short wavelength to very long wavelength. And what I want to show you is the light that reflects off of the object has to be equivalent to the size of the object in order for you to see it. What it means is if you want to capture a human figure, the light reflecting off has to be somewhere in the microwave to radio wave wavelength. Or if you need to see an atom or a molecule, you would need X-ray, which is 10 to the minus 10 meters. What we have at the FEL is very short wavelengths that allows us to look at single molecules or single atoms or even single electrons moving. And what comes with the size of the objects is the speed of how fast they're moving. So the smaller the object becomes, the faster they move. So here on the right side is a horse. And I'm sure a lot of us take pictures every day. And if you use your personal camera, what you can see is how fast a horse is moving or how fast a bird is flying. But when you need to see something smaller, such as how the proteins are folding or what is happening in your body, you need something called X-ray. And what we have at the FEL is an ultra-fast and an ultra-high precision X-ray camera that allows us to take pictures of very small and very fast-moving things. So what this eventually allows us to do is to look into detail of what the electrons and the atoms are doing in each of these new materials that have the potential to enable us to build future quantum technologies and fusion energy applications that allow us to power the grid of an entire city or of the whole world, which hopefully happen in many years to come. And before I start talking, showing you some very exciting results, let me tell you what the experiment looks like. So we start from 3 kilometers away, first generate many bunches of electrons. At some point, they get converted to photons, or in another word, X-ray. And this X-ray goes into the experimental hudges. Here's the person with one of the very complicated instruments with hundreds or thousands of cables. And each hudge is the size of a basketball court, even bigger. So imagine how many cables we have there. So everything has to be controlled from an external room, also for safety reason. So each of the TV screens that you see here is about 70 inches, and we look at 8 or 9 of them all at once. So if you've seen one of these NASA launching rocket movies, it's sort of the same thing. So now if I zoom into the exact experimental setup that we're interested in here, it contains a lot of very complicated optics and crystals that lead the X-ray and the laser to the experimental setup. And what we do is we have a 3D robotic detector that moves around and captures the signal that comes out. So in this case, what happens is I use an ultra-fast laser where I give an electron and an atom a kick. It resembles what happens when you use your phone and it gets really hot, or when you use your laptop or any electronic devices, it gets really hot. It will change the properties of the material. We want to make sure that the material behaves the same way, and we still have high functioning electronics. So now the laser does what it needs to do, and the X-ray acts as the camera that comes in and takes pictures of how the electrons and the atoms respond. So in order to carry out one of these experiments, which it does take quite a long time. So first, anyone from or any institution from the community can submit a proposal, and if the proposal is accepted, it's about a year of preparation to work with the scientists and the engineers to conceptualize the idea in the proposal, discuss the scientific questions, and build up the entire experimental setup. And then by the time comes to do data, then we start doing, hopefully, data collection if everything is prepared very well, which typically is or does. And then it produces hundreds of terabytes. We have to do a lot of data processing, and up until this point, due to the limit in computational time, we can only look at 10% of data in real time. And then from there, we extract important insights and make decisions. So it typically involves a lot of people in this process, and the whole thing from step 1 to step 4 has to be done within 60 hours, over 5 days, so 12 hours for each. So we make these decisions very quickly to keep steering the experiment, because each of these is on the order of millions of dollars. And then after doing the experiment, it takes multiple years to lead to publications going from computation, data processing, data analysis, comparing with theoretical calculations, and then write up a paper. So let me tell you why the data is so big. So here in this case, we specifically use a 2D pixel detector called Jungfrau. So it's made from the Porsche Institute in Switzerland. And a lot of things that they make, they name each of them after a mountain. So Jungfrau is a mountain in Switzerland. And what happens is it can collect, or we collect data in different fashions that create multidimensional data. So for example, one axis is momentum, which basically map out the whole materials in 3D space. And another is in time to see how the electrons and atoms are moving, and also the intensity of the movement. So right now, with the current linear accelerator called LCOS, which stands for Linear Coherent Light Source, we produce hundreds of terabytes over 60 hours. We have ramped up to a new light source called LCOS2, which just got commissioned, and it's a 10-year project by 6, 7 different Department of Energy laboratories over the course of 10 years. And this new LCOS2 will generate on the order of petabytes data scale. So I'm sure most people in this room are familiar, but basically petabyte is equivalent to someone waking up every day and take 4,000 pictures per day for the rest of their life. Or if I put 1 gigabyte flash drive next to each other, a petabyte size data would take up 92 football field size. That's how big it is. So now we have to figure out what to do, because we cannot analyze data fast enough. And if we don't see what we're doing, then we're completely blind, and it defeats the purpose of doing discovery science. So let me quickly tell you what is in the data and why we care so much. So here is the detector screen on the left. And on the right is the signal extracted from each of these locations. So now we go into a signal processing, a signal decomposition and signal processing problem. So if we decompose these signals and understand each of them, then we know exactly how the electrons and the atoms are moving with respect to each other. And that is what we're looking for. And we know how the entire materials behave and how the properties behave. So oftentimes, we calculate ahead of time what we will see, how we set up the experiments, and where the signal will be. But then when you show up to an actual experiment, this is often what you see. It's a whole lot of nothing. So as a grad student, or when I was a postdoc, I sat there and I was extremely disappointed at a lot of things because there was no signal. So what do you do when there's no signal and there's a huge time pressure? So we basically brute force and look around at different areas on the detector using NumPy and SciPy primarily, and try to really find each of these signals. And each process does take a long time that exceeds over the time limit for each shift. But luckily with cuPyNumeric, we can parallelize a lot of these tasks. And what happens is we can look at the entire detector. Here is just a section, and I'm giving an example where you have huge signals so you can see what I'm saying. So basically, if I zoom into each of these spots on the detector, I should see completely different signals. And what it means is the atoms are moving in completely different ways. And that's the information that I need to know. And then I can run all of this in parallel. And instead of, spoiler alert, so instead of taking more than 10 hours to look at the full detector to find the signal, now it takes 4 minutes. So it's a lot faster. And I can get live feedback to keep steering the experiments. So how do we actually do this? So maybe Andy showed this on Thursday, I cannot remember. But cuPyNumeric is basically a NumPy library that operates on multi-nodes and multi-GPUs. And it's built on top of the Leagate framework that came out of Stanford, and it allows implicit parallelism. So what it means is instead of having to do lengthy coding using NPI and partitioning code, now you import cuPyNumeric at NumPy and really shorten your code to do the same purpose. And then how do you submit it to these different computer clusters? So you basically do a very similar submission routine, where you specify the number of nodes, the number of GPUs to a handful of supercomputers that we have demonstrated up until this point. And this tool is extremely useful because it allows many scientists and engineers at different levels to code and run on supercomputers and not just computer scientists. And what we have done is we have built cuPyNumeric on a number of different supercomputers, including internal NVIDIA, 2 DOE supercomputers, and SLAC and Stanford internal computers. And what we've seen is a really high speed up of about 180 times, and it allows us to complete the full detector analysis from 10 plus hours to 5 minutes. What this means is the entire beam time generates hundreds of terabytes, but after compression, it becomes about 7 terabytes. So now we compress the analysis time solely from more than 7 months to more than 1 day, which is a huge improvement. And what this does is it enables us to get feedback during the experiment and train digital twins to run experiment live and give live feedback to keep tuning the parameters instead of having to run in blind. And the long-term impact is it will compress the publication's time substantially by performing computations very quickly. So hopefully I have conveyed to you the power or the benefits of X-ray free electron lasers such as LCOS2, and how cuPyNumeric working with LCOS2 can build a very comprehensive tool to allow us to look into different kinds of science, ranging from planetary to materials to biology and chemistry, and provide new insights that we have not seen before. And with that, I want to thank the folks that also work on this, Irina and Malte at NVIDIA, and Seshu and Yana at SLAC National Lab. With that, thank you, everybody, for being here today.
Thank you, Ko, for this wonderful session. So we have some time for Q&A. So please use the mics behind to ask the questions, and please try to keep it brief.
Apparently, I gave a very clear talk.
Yeah.
Nobody has questions.
Then let's give it more round of applause for Nguyen.
I did have one question.
Oh, sorry.
When you were comparing the times for like NumPy or the cuNumPy versus what were you comparing it to? Were you using like NumPy or a different product to do it versus like concurrent futures?
Yeah, so I basically wrote all of these analysis Python codes, or all these codes in Python already. So we ran that exact same procedure on CPUs. And on the cuPyNumeric, we changed the code from NumPy to cuPyNumeric, and then ran it on multi-nodes and multi-GPUs on each of these, and we did the exact same thing for each of these clusters, or supercomputers.
And then compared to like any of the other ones, or did you just purely compare it to NumPy?
Purely compared to NumPy, yeah.
Okay.
So right now, so cuPyNumeric only contains NumPy libraries, and that's available at this point, yeah.
Okay, thank you.
Thanks.
How easy was it to change your code base from using NumPy to cuPy? Like, was it a week, a month? Was it pretty straightforward?
How honest do you want me to be?
I mean, you're somewhat realistic. But
It's not easy yet. Hopefully
Okay.
it will be more easy in the future.
Okay, I've considered it in the past, and it was like, it's close enough, but maybe not quite. Okay, thank you.